We stated earlier that for a reversible process that the entropy change is going to be 0, and for an irreversible or spontaneous process the entropy change will be greater than 0. So for this inequality, which defines the second law of thermodynamics, ds is greater than or equal to dq over T, the differential of heat over temperature, for giving us the differential of entropy, that equality case ds would be equal to the heat of a reversible process divided by the temperature. So claiming here that we have a 0 entropy change for a reversible process, let's go through the two examples of reversible isothermal expansion and compression and reversible adiabatic expansion or compression to see that this really is the case for those two processes, just to demonstrate that this is true. Okay, so we're going to start out with reversible isothermal expansion. Remember, isothermal, the temperature staying the same across the entire process. So some reversible isothermal process. All right, our total entropy change, delta S, is going to have two parts. We're going to have delta S of the system plus delta S of the surroundings. That will give us the delta S of the universe, which is an isolated system, so the entropy change must be greater than or equal to 0. And let's see that it's 0 for the universe. And as I said, T is constant for any isothermal process. Okay, so our delta S, since T is constant, can be defined as the heat of the system over temperature. That'll give us the entropy for the system plus the heat of the surroundings over temperature. That'll give us the entropy change of the surroundings. And as we said for a couple of videos ago, for the expansion or compression of a gas, the entropy change for that process, we derive that ends up being nR log V final over V initial. But let's remember that whatever the heat of the system is, the heat of the surroundings is equal and opposite to that. So, and they're also going to be at the same temperature there. So that is going to mean that the entropy for the surroundings, which is input, or which is going to go down if the system expands, or it's going to go up if the system compresses, the opposite case. Those two are going to be equal and opposite, and they're going to sum up to 0. So this is only true because that was reversible. If we did that in a reversible way, then there would be more work done and there would be less heat input, and so this value wouldn't be as large and it wouldn't cancel out. But this value only is as large as this value when it's done reversibly, which is doing the minimum amount of work during an expansion and doing the maximum amount of work during your compression. And again, that was true because during this isothermal process, Q sys equals minus Q surroundings. So our net is that delta S equals 0. All right, and for the other case, not sure why that keeps coming up red. For the other case, reversible adiabatic expansion, or compression, expansion, compression, process, pick your favorite word. We said that for that case, we're going to have Q equals 0. So Q system and Q surroundings are both going to be 0. So the net result there is that delta S, which again is the sum of the system entropy change plus the surrounding entropy change, is going to be 0 over T, because that Q is 0, plus 0 over T. And of course, 0 in both of these numerators here. That is going to give us a net of 0. So our delta S is going to be 0. And this confirms that for both of these processes, both of these reversible processes, they confirm that what the second law predicts, this equality that ds equals 0 for a reversible process.
Saya Yanto, grafik kelompok 11 ingin menjelaskan mengenai video lantaran kami ambil, yaitu pertama proses irreversible dan proses reversible untuk perubahan entropi. Pada perubahan entropi untuk irreversible proses itu ds lebih besar daripada dt per t. Artinya pada proses irreversible perubahan entropi itu selalu naik. Untuk proses reversible, perubahan entropinya ds sama dengan dt per t. Artinya di sana untuk proses perubahan entropinya itu selalu konstan. Untuk proses irreversible ini terjadi pada proses termodinamika seperti isotermal, adiabatik, isokorik sama isobarik. Yang pertama, proses reversible untuk isotermal. Pada proses isotermal, T sama dengan konstan. Artinya di sini suhunya konstan. Maka untuk perubahan entropinya itu memenuhi persamaan ds sama dengan delta S sistem tambah delta S lingkungan. Untuk persamaan delta S nya itu sama dengan delta Q per D sistem tambah delta Q D lingkungan. Untuk rumus Q pada proses isotermal itu sama dengan Nn dan 2 per 1. Di sini ada pengecualian ketika sistem melakukan kerja, maka nilai Q-nya sama dengan min. Jadi untuk di sini sistem dia yang melepaskan kerja dan yang ini menerima kerja, maka di sini dia melakukan kerja, di sini nanti minus. Maka sama dengan kita substitusikan persamaan tadi menjadi Q menjadi N R dan V2 per V1 dikurang karena dia melakukan kerja dan V2 V1 ya. Maka ketika dia melakukan kerja kita mengambil di sini sehingga persamaan delta S sama dengan minus N R dan V2 per V1. Ini untuk delta S sama dengan 0. Artinya perubahan entropi di sini konstan di NR dan V2 per V1. Selanjutnya itu proses adiabatik. Pada proses adiabatik di sini perubahan entropinya itu tetap memenuhi persamaan ini. Namun pada proses adiabatik delta Q sama dengan 0. Maka delta S sama dengan delta S sistem ditambah delta S lingkungan. Maka ini sama dengan delta I per D sistem ditambah delta I lingkungan per D. Tadi delta Q sama dengan 0. Kita substitusikan 0 per D kurang 0 I ditambah 0 per D sama dengan 0. Delta S untuk proses ini sama dengan 0. Demikianlah dapat saya sampaikan mengenai video yang saya ambil itu perubahan entropi pada proses irreversible dan irreversible pada isotermal dan adiabatik.
In this video, I'm going to go over how to calculate the change in entropy of an isobaric process. And so isobaric means constant pressure. Constant pressure. And so on a PV diagram, a gas undergoing an isobaric process would start at, we would have, say, let me just rewrite this graph. So it would look like, oh, that's still terrible. One more time. Bit better. Okay, so we would have, say, pressure 1 from state 1, and we would have a gas going from state A to state B, and this would be constant pressure. Now, to calculate the change in entropy of this, it depends on, well, we have to know the definition of the change in entropy, and that is delta S, where S represents entropy, is equal to delta Q over T. And this holds true for reversible reactions. Reversible reactions, not irreversible reactions. And it's actually quite simple. All we have to know is what equals the change in Q. Now, for an isobaric process, we know that the delta Q is equal to the number of moles times the ideal gas. This is for an ideal gas. Cp times the change in temperature. Now, if we wanted to take the derivative of this, because these are constants, it's just a constant times the derivative would be here and here, we get dq equals n times Cp times dt. Now, if that equals dq, then we know that dq over t will equal our change in entropy. So we can rewrite this. This is delta S equals, and we just substitute in what we found for the derivative of q, which is n Cp times dt over t. And what we can do here is if we integrate the dt over t, we can write delta S equals NCP times the natural log. We take the natural log, then we get natural log of T2 divided by T1. And now this can also be written as natural log of T2 minus the log of T1, and that's the same. This is the same as, this thing here is the same as this, and it's just the same because of logarithm rules. So overall, that is how you calculate the change in entropy of an isobaric process, or constant pressure process.
Baiklah, dalam kesempatan kali ini, saya Rizka Indrianti akan menjelaskan mengenai proses isobarik dalam entropi. Nah, kita ketahui bersama bahwa proses isobarik itu memiliki tekanan yang konstan. P sama dengan konstan. Sehingga, jika kita gambarkan dalam diagram PV, mesin nilai P, mesin nilai Q, maka di sampingnya D itu pada proses isobarik, saya di sini titik A ke titik B. Dia konstan, P-nya konstan. Nah, selanjutnya kita tahu bersama bahwa rumus umum entropi itu adalah delta S sama dengan delta I per T. Nah, untuk kita ubah ke dalam proses isobarik, kita harus tahu dulu persamaan dari delta Q. Di sini delta Q itu pada proses isobarik adalah jumlah mol, banyak mol dikali Cp dikali delta T. N kali Cp ini merupakan konstan, sehingga rumunannya kita bisa buat dq sama dengan N kali Cp dt. ini kita ganti jadi N dikali CP dikali dt per T. Nah, selanjutnya yang bagian sini kita integralkan. Delta S sama dengan, kita tahu tadi kalau N kali CP itu merupakan konstan, sehingga N kali CP integral dt per T. Ini kita kasih bawahnya T1 dan batas atasnya T2. Sehingga diperolehlah nilai entropy N dikali CP dikali dt per T itu adalah ln T2 dikurang ln T1. Pada persamaan logaritma atau rumus dari logaritma, ln T2 dikurang ln T1 itu dapat kita tuliskan sebagai kali logaritma natural T2 dikurang logaritma natural T1 dapat kita tuliskan ln T2 per T1. Jadi ini merupakan rumus umum untuk mencari nilai entropi pada proses isobarik.
In this video, I want to talk about how to calculate the change in entropy of an isochoric process. An isochoric process is a process that has constant volume. Constant volume. On a PV diagram, it looks like this, where we have a, say, volume 1, and we could have a gas that goes from state A, we add some heat, and it goes to state B. And that's it. This would just be an isochoric process. Now, before we can calculate the change in entropy, we have to know the definition of the change in entropy. And that is delta S equals delta Q over T. And this holds true for reversible reactions only, not irreversible reactions. Now, to calculate the change in entropy of an isochoric process, first off we have to know, it's very simple. All we have to know is what equals the delta Q. Now, with an isochoric process, because none of the energy that we're adding gets turned to work, we know that delta Q equals the delta of energy. And so the energy equals 3 over 2 nRT. And so if we wanted to find the derivative of this, we know that this is constant, so it's a constant times the derivative of this and the derivative of that. So it becomes the derivative of E equals 3 over 2 nR times the derivative of T. Or like the infinitesimally small change in T. And so from that, we know that delta S, since delta S is delta Q over T, and delta E is delta Q, delta Q equals delta E, then what we can write is delta S equals the delta Q, which was 3 over 2 nR times dt over T. Remember, because we have the T here. Now, what we can do is we can integrate this, and we can make it quite simply. We just go, the change in entropy is equal to 3 over 2 nR times, and see, for here, all we have to do then is go the natural log of T2 divided by T1. Or we could write that as ln T2 minus the ln of T1. This is the same, it's just logarithm rules. And basically, this is how you calculate the change in entropy of a isochoric process or constant volume process.
proses yang terjadi pada volume konstan. Tadi telah dijelaskan bahwa persamaan umum pada perubahan entropi yaitu delta S sama dengan delta Q per T, di mana delta S merupakan perubahan entropi, delta Q merupakan perubahan kalor, dan T merupakan suhu. Nah, seperti yang telah dibahas juga sebelumnya, pada isotorik delta Q bernilai sama dengan delta U atau delta E. Nah, dari teori kinetik gas kita ketahui bahwa nilai energi itu merupakan 3/2 nRT. Kemudian kita diferensialkan kedua sisinya menjadi dt sama dengan 3/2 nRdt. Mengapa suhu yang kita diferensialkan itu dikarenakan 3/2 nR merupakan konstanta, sehingga ini suhunya yang kita diferensialkan. Kemudian ini kita masukkan ke persamaan ini sehingga didapat delta S sama dengan 3/2 nR dt per T. Nah, ini kita integralkan sehingga didapati bahwa perubahan entropi pada proses isotorik yaitu bernilai 3/2 nR seper T dt